Okay, so in this video, we're going to introduce two specific sorting algorithms for solving this problem of sorting. So both of these algorithms are going to use a strategy to solve them. We are calling this the iterative improvement strategy. This isn't a formal term that people use broadly. It's just a term we use in 373. But the idea is that you maintain an invariant that you iteratively improve over time. So each step of your algorithm kind of gets you closer and closer to solving the problem in whole by kind of relying on an invariant you already established. So what we'll do is in these algorithms is kind of have what we call a sorted region of our array, where we're kind of, here are all the things we already have sorted, and we will rely on that kind of subarray that we've already processed as already being sorted in our sorting algorithm, and then kind of increase that subarray by 1 each time. This kind of iterative improvement invariant is after k iterations of our sorting algorithm, the first k elements of the array will be sorted. And how we use that is an implementation detail in both of these algorithms that we're going to learn in this video. So let me show you our first algorithm, which will make this idea a little bit more concrete. The first algorithm is called selection sort. So here is an array, and I haven't explained how to do all the selection sort yet, but to get in our head a bit, to think about this idea of we have an invariant that's already true, our invariant said after k iterations, the first k elements will already be sorted. And so let's just start in the middle to understand what selection sort does, and then I'll explain the full algorithm from scratch. Which is we start with kind of our left-hand side as a subarray of already sorted items that I use blue for. I'm going to use the same colors throughout the slide. Then we kind of have this kind of current item, the next item we need to deal with in our kind of iteration. So we're kind of moving through dealing with one item at a time. And then we have this unsorted region, this pink section that we kind of don't have any idea about the sorting for. And the idea is to kind of decrease the size of that by 1 each time we're processing an element. So each iteration of our algorithm, we kind of increase the number of sorted items by 1 and decrease the number of unsorted items by 1. So the process for using this, we have this sorted array. And again, I'll tell you how we get there later. But let's just suppose we're starting with this invariant. We suppose it's true. Let's just make sure it's true after. Selection sort operates by kind of going through the rest of the array, the stuff that we haven't sorted yet, and finding the next smallest number, and then kind of swapping that with the current item. So we currently have 2, 3, 6, 7 in our sorted section, and we have 18, 10, 14, 9, 11, 15 everywhere else. So selection sort will kind of start at 18 and look through the rest of the array for the next smallest number. So it's going to scan all of the values from the current item and all of the unsorted items and find the one that is smallest. So maybe it'll have to like keep track of an index during this loop. And it finds that 9 is the smallest number in this kind of region of the array. And then we just swap. So we swap the current item with that index of the next smallest number. And now once we've done that swap, since 9 was the smallest number remaining in this unsorted items and the current item, that is going to kind of go along with our sorted section. And then so we just repeat. So now we go to the next number and we say, okay, start here, find the next smallest item. So in this case, it would be 10 itself, and we swap 10 with itself and kind of increase our sorted items by 1. So selection sort is kind of going through and finding the next smallest thing at a time. Now, to give you a bit of a slightly different intuition for this, think if I was trying to sort a stack of exams, like actual physical paper exams. The selection sort strategy is look through all of the exams to find the one that comes alphabetically first, assuming my ordering relation is by your name. Find the smallest one and put that in the front. Then take all of the other exams that I currently have. I've only sorted 1. Take all the remaining n-1 exams and go find the next smallest. Grab that and put it behind the first one. And you just keep going to select the next smallest thing and putting it at the end of kind of your sorted region. That is what selection sort is doing. The kind of pseudocode for a selection sort is we start kind of for each kind of current in the list, we're going to go find the next smallest thing starting at current and then swap it with kind of where our current is. Now, notice what this means is that this sorted region of items starts out as empty. So we start off this algorithm having no items that are sorted. And so this find next min is going to go through and find the globally smallest value in the whole array and add that as our first item in our sorted area. So how would you implement this find next min? Well, you start at the current and then you loop through all the other unsorted items. Notice I'm color matching here, where I'm using the color red to talk about the unsorted items. And then if we ever find one that's smaller than the current item, we kind of keep track of that. Notice this is pseudocode. It's not real Java code. So there's probably some extra details about keeping track of indices and stuff like that. But once you find the next smallest item, then you just swap them. And we do this over and over and over again. Each time we find the next smallest value from the rest of the array and stick it at the end of our sorted region. That's why we swap. The current item is right after the sorted region. And so we swap the current item with the next smallest number to grow that sorted region by 1. So now the question here is, well, how does this algorithm perform? What is the runtime of this algorithm? So the worst case runtime, well, if each time I need to go from the current item and go all the way to the end of the array, and each time I increase my sorted items by 1, meaning I can move the current item over by 1, the first time I have to iterate n times, and then n minus 1, and then n minus 2. Each time I have to do this find next min, I have to scan from where I am to the end of the array. Whenever we have this kind of, in some sense, nested loop pattern, where you do kind of I things n times, where you kind of are iterating I from 1 to n or from n to 1, then we kind of get this n squared runtime. Just like when we have this for I is equal to 0, I is less than n, for j is equal to 0, j is less than I, right? That kind of pattern, we saw that n squared, 1 plus 2 plus 3 all the way to plus n, which is something like n times n plus 1 over 2, or big theta of n squared. What about the best case runtime? Well, I would argue that selection sort doesn't care about the actual values in the array, right? It doesn't stop early on any of its find next min calls. It always has to scan the whole array to go, or the array starting from current, in order to find the next smallest thing. So it doesn't matter if your array was already sorted or reverse sorted or anything. Every iteration of this algorithm is going to take the same amount of time regardless of what the data looked like. So the best case is also going to be n squared. And in practice, meaning kind of what we expect to see, is going to be something close to n squared. The in practice case, like before, is going to be a little bit hand wavy. You'll just have to believe us. But I'll tell you that in practice, you'll see this thing run big theta of n squared. This will usually, we'll start seeing different in practice runtimes on Wednesday when we start talking about algorithms that use randomness a little bit in their runtime. So the question is this sort stable? The answer is, it turns out, no. This will not guarantee a stable sort. It's a correct algorithm. It will always output a sorted list, but that sorted list may or may not be stable. I'll explain that on the next slide. And then there's one other term that I actually didn't introduce in the last video, which is this concept of in place. When we ask if an algorithm is in place, means that it could just do it in the input, do any of the modifications in the input array. It doesn't need to create an extra data structure outside of the array in order to solve it. And I would argue that this selection sort is exactly an in-place algorithm. We always are just swapping values inside the input array. So let's understand why selection sort is not stable. It has to do with the fact that when we do these swaps, that you can swap values in arbitrary places in the array, essentially. So for example, suppose I had this input array, and I'm marking the two values 5a and 5b as suppose they're like some complex data type like movie, and we're sorting by name. Well, they have the same name in some sense, but there's another way of distinguishing them. So 5a should some sense come before 5b in a stable sort because it shows up first, but we're only sorting based off the number 5 or 3, 4. And so the first iteration of selection sort from this array starts by scanning from the beginning, current item being the first item, start from the beginning, go to the end, and find the smallest value, and then swap them. But notice, because 2 might have been really far in the array, then 5a now appears after 5b in this iteration, And so in the final sort, it might end up with 5b coming first. And so since in a case of a tie, where they both have the number 5, we didn't preserve the input ordering, it's not guaranteed to be stable. So we would not say that this is a stable sort. That's selection sort. Kind of scanning through, finding the next smallest, putting it at the end of your sorted region, which increases your sorted region size by 1 each time. And you can see if we do this n times, you'll now have a sorted array of length n, your input array. So that's one algorithm. Now I'm going to introduce another algorithm. In some sense, kind of selection sort's evil twin brother or sister. Kind of very similar idea, but that makes one weird twist that makes it look a lot different. So insertion sort has the same setup as before. We're still using this iterative improvement invariant. However, how we use this invariant is going to be very different in insertion. So insertion sort, instead of scanning through the entire unsorted items, looks at the next item, the current item, and finds the proper place to put it in the sorted array. So before I show you an example with the array, let me give you that intuition of exam sorting. This sorting strategy is, instead of searching through the entire stack of exams for the next smallest thing, keep your kind of currently sorted set and take the next exam and put it in the right place in that smaller sorted set. So just grab the exam off the top and stick it into your sorted region wherever it properly belongs to keep that sorted region sorted. So instead of scanning through all the unsorted arrays, we just grab the current item and find its right spot in the sorted items array. So we say, oh, well, 5 is less than 7 and is less than 6. So we go find its right spot. Oh, it should go at index 2. And so then we kind of move the 5 before the 6 by shifting the 7 and the 6 over. And now we've increased our sorted region by 1. And so now we just repeat this. So find this next spot, and it might end up exactly where it's supposed to be. So we just increase the size of the sorted items by 1. But we're always just grabbing the next item and finding the right place in the sorted region. Notice this is like the opposite of selection sort. Remember, selection sort had to search the rest of the array, all of the unsorted items, for the next smallest value to swap with the current. And because it's the next smallest value, we don't need to figure out where to put it in the sorted items. It's just going to be greater than the previous smallest value. But with insertion sort, we never scan the unsorted array on each iteration. We just grab the current item and then go stick it or insert it in the right place in our sorted region. So insertion sort is going to look somewhat similar in terms of the pseudocode, but has, in the sense that you're just repeatedly kind of doing a task, but the details are very, very different. So now notice that in my pseudocode, I'm using a different color. I'm using blue because we're working with the sorted array, not the unsorted part of the array. And we say, okay, we'll take the current item and find the right spot for it. So go through all of our sorted region and find the proper spot. And there are implementation details for how to do this. We described it as starting from the end and kind of working your way towards the front to find the proper place. And then once you find that index, shift everything over so that you can put the 4 or the current item in the right spot. So that's the idea of insertion sort. You have your sorted section of the array. You just grab the next value from the unsorted section. You don't need to find the smallest, just any of them. Grab the first one and then stick it or insert it in the right spot. While selection sort needs to go select the next smallest value to put it at end. Very tiny details or change in details can cause very drastic change in how the algorithm actually runs. So I would argue, just like with selection sort, insertion sort is going to have this worst case big theta of n squared runtime, right? We have to do a lot of shifting. So in the worst case, we might have to shift n elements, like shift the entire array every single time, maybe always inserting in the front. In that case, you're going to be shifting n things, n times, or kind of that increasing sum, and that's going to give us something like n squared. But the best case is a little bit different. So for a second, what is the best case for this algorithm? What is the best case array that we can get for insertion sort? Take a second and think about that. what if the array was already sorted? Then for each current item, we ask, oh, where do we need to insert it in the stuff before? Well, it's already in the right place. And so we don't have to do any shifting. This shifting and find spot would be an O of 1 operation. And so then the overall work is just going through each element and figuring out its right spot. It's exactly where it is. So it turns out in the best case, with an already sorted array, then we have this kind of nice runtime of O of n, or big theta of n. And you can imagine that theoretically, kind of in practice, you might see some speed up because you might have sorted sections of the array, or maybe it could potentially be mostly sorted, but not completely. You can't necessarily guarantee any of that. So in practice, we'll still see this big theta of n squared. It's sometimes nice. It could be slightly more efficient sometimes, but in the worst case, and technically in practice, we'll still see this n squared runtime. Now, I would argue to you, though, you almost always will use insertion sort over selection sort. Why? Well, sometimes you might get this best case, and also with insertion sort, it ends up being a stable sort. Now I will explain that on the next slide. And just like with selection sort, since we're just modifying the array we're working with, it's also in place. So why is insertion sort stable? Well, all of the swaps are going to be happening with adjacent items. Like when we're shifting, we're kind of just shift, moving everything over by one spot. The duplicates will always be compared against one another in their original ordering. So if we had this kind of, we start with this same array, 5a, 3, 4, 5b, we start by inserting 5a into our sorted section, and then we insert 3, so it goes before 5a, and then we insert 4, which goes before 5a and after 3, and then we insert 5b into our array, and if you get your details right, if there was ever a tie, you would add it after, kind of the one that was already in there, meaning that you preserved the kind of overall ordering. So insertion sort will end up being stable. So that is kind of the reason why people generally prefer insertion sort over selection sort. Even though they're very, very similar algorithms, almost confusingly similar. It's really hard to tell the difference between them when you're first learning this. Insertion sort is only in some sense strictly better in a lot of ways because it has potentially a better best case, and it's also a stable sort. So this kind of last slide for this video is kind of comparing the two kind of on one place. Selection sort is looking through the unsorted array to select the smallest item to replace with the current item, and then we swap them. While insertion sort looks through the sorted values to insert the current item in the spot where it belongs, and then we have to shift everything because it's an arrays. Now, we said just before that people tend to prefer insertion sort because it's stable and can take advantage of data that's already sorted, which is actually not the most common or uncommon thing. It can happen kind of commonly where people have partially sorted data. Maybe the data source they're getting it from already has some sortedness to it, or they might have already ran a different sorting on it and they could have lined up. So it's not guaranteed to be faster, but it might be. It could only potentially be faster. Also, it allows you to use a linked list implementation, which now makes it easier so you don't have to do any shifting, which can be a slight speed improvement, but that's mostly constant factors, not necessarily asymptotically faster. I tried to think of some reasons why you might use selection sort over insertion sort. The only one I could really think of is it minimizes the number of times you have to write to the array. Because with insertion sort, you might have to be doing the shifting operation. You have to move a value over a bunch. So if for some reason writing to an array was slow on your computer, then maybe selection sort would be better. But for the most part, defaulting to insertion sort seems like a reasonable thing to do. Now, in the next video, we're going to introduce one last sorting algorithm for today, which uses a kind of slightly different approach to how to solve this task.